Hello YouTube viewers, welcome to my channel Science to Technology. In today's show, Rocket Monday, we're going to talk about landing on moon, specifically focusing on Chandrayaan 3. So let's dive deep into it. So what is its path? This puppy was launched and it has been launched successfully, so we are good. It's in space as of now. So this puppy was launched in 14 July 2023, 14:35 Indian Standard Time, and Universal Standard Coordinate Time would be like 9:05 early morning, so to say. Now, launch vehicle Mark 3 was used. GSLV Mark 3 has been renamed Launch Vehicle Mark 3. Now, to have the telemetry support, radio support, basically European Space Tracking Asset has been used. Basically, ES-Track is being used. Basically, we are in consultation with ESA for telemetry and all that. Just it happens as a common thing because you may not have radar station exactly where you need to, telecommunication standard exactly where you need to. So sometimes countries collaborate for this. And Vikram lander is 1.7 ton object, as in Big Daddy. You're talking about 1752 kilograms. And Pragyan rover, this rover is also huge, it's 26 kilograms, so quite a competent stuff. Now, target landing date is 24 August 2023. Now, be mindful, this is targeted landing date, does not mean it will happen exactly that. It could be delayed by 15 days or 20 days. If they detect something where it's like, you know what, it's suboptimum, they can delay it. So don't hold your breath for that exact moment, but this is the optimum time as of now. That will be at late 6-7 p.m. of Indian time, and it's using bi-elliptic transfer orbit. Now this is basically you are creating two ellipses. One is going away from Earth, another is going to the moon. Benefit of this is it consumes very little fuel, does allow you to transfer far more bigger payload. Again, that's almost a small car, so it does have benefit. Consequence, it does take time, as in like 45 days to 48 days. Now, India has this rocket. This is the biggest rocket India has that is functionally active. So we have to okay, how is the best thing, how to get best bang for the buck for this rocket? Could they have made sure that this reaches moon in, let's say, 3 days? Maybe. It can be done, but here's the payload would have shrunk to almost lol. So for that reason, this path was chosen, and it's a kind of common thing. Whenever you want to go to basically moon for low cost, you always do this. So you you go to low Earth orbit, you make an ellipse, you boost again, make an even bigger ellipse, boost again, even bigger ellipse, boost again, even bigger. You keep doing it multiple times. Then you do moon capture, then moon captures you, then you literally shrink in reverse. So you have a first very large ellipse, then you slowly, you will start very large ellipse, then you start to slow down, then you will try even more slowing down, you brick by brick comes to very close to the basically orbit of moon, very close, like hundreds of kilometers close. So this is how it works. Now, once they have landed, because lunar day is much longer than Earth's day, it's supposed to work for 14 days continuously. Now be mindful, there is no night there, so as in there is, but in that location it will be like day for 15 days, night for 15 days. So if they do it correctly, they should get 14 days of continuous working without any issue. Since they are not using any radioactive isotopes to heat them, that 14 days of darkness will most definitely freeze this puppy over. So it's very unlikely that after that day they will work. So everything has to be done in that 14-day time period. Benefit, it's continuous 14 days. It's not like, okay, day and night and all that. It's continuous. So this is the path of the mission. Now we cannot talk about Chandrayaan 3 without understanding Chandrayaan 2. Now Chandrayaan 2 was launched on 2020, pardon me, 22 July 2019 at 14:43 Indian Standard Time, and it was successfully, safely launched. So we got everything was fine there. Then it reached moon on 20 August 2019. Everything was fine. Everything was awesome. In 06 September, it tried to, the Vikram, basically the lander part, did a landing. Now it failed. Now it did everything it's supposed to do except the softly landing part. It went there, it just bammed. So it crashed. However, that being said, even though the lander failed, the orbiter was fully successful. There were two parts of the mission. Orbiter did its job flawlessly. It got into the orbit, it started to do, and it had multiple tools, like a very long list of tools, and all of those tools were working. Chief among them was this puppy. Now this puppy is the highest resolution lunar reconnaissance optics as of now that is there in lunar orbit. This puppy has partial resolution of 25 centimeter per pixel. This is highest as of now. When I'm recording, this is the highest, and this actually helps us to plan out for Chandrayaan 3 with much higher resolution. And be mindful, moon does not have as active of an atmosphere as Earth does. Now it does have some atmosphere, which is like, I don't even think PSI is a good enough measurement to count that, but very tiny atmosphere. So from its vantage point of view, it's almost a raw vacuum. So it's looking at the surface and it can get really actually resolving power of that. It's not just like, okay, mathematically it's 25 centimeter. It's like, can you build something like this in Earth? Yes, but the Earth's atmospheric shimmering will make it black. Here there won't be something like that. So it's really useful for us, and all the scientific objective that was set for the orbiter done. Everything's fine, everything's good. So this is from Chandrayaan 2. So we had to learn from what exactly went wrong. Well, as usual, moon is the graveyard of software. So software failed. Now hardware worked more or less the same, meaningly they fired the rocket engine did more or less what it's supposed to do. However, errors started to pile up. What does this error mean? Error simply means whenever you are giving a command, you are expecting a certain output, meaning I'm going to trigger the rocket engine for, let's say, 50 seconds. I'm expecting this sort of decel value. Basically, I'm decelerating in this sort of value. Okay, that's fine. But here's the deal. What if the value is a bit more than you are expecting or a bit less than you are expecting? That's what we call error. There is always some tolerance data. However, whenever Chandrayaan 2 did any mission, things were little bit off, just a little bit. It was not triggering a red alert, but it was just a little bit off. Consequence of that, those little things started to pile up and it glitched the system. Just before the landing, it glitched the system so hard, it was like, I have no idea what the hell is happening. It crashed. So to simplify, what exactly went wrong? This is the data that I'm giving you here is directly from ISRO's chief. I have linked the video down below. It's basically Chandrayaan 2 was success-based software. And success-based software simply means I'm going to fire the rocket, it's going to give me this amount of decel, and I'm going to, plan go to the second. There is no fail safe where it's like, oh, I fired this, it did not work as I expected, then what should I do? There was no, it was success-based basically. However, in Chandrayaan 3, it's completely what we classify as failure-based design, meaning you fire the rocket, let's say it only gives you 50%. You will not stuck out. You will not glitch out. You will figure it out. What can you do? What are your options? Everything has what if, what fails, what to do, how to solve it. Basically, the software of this time is far more laxed, where it's like, my job is to land on the moon surface, nothing else matters. Like, oh, my rocket engines are not working adequately, no problem, I'll still do what I'm supposed to do. Oh, my spin vectors are much higher, no problem, I'm still gonna do what I'm supposed to do, or try my best to do what I'm supposed to do. And this is why this time the landing struts has been reinforced to make sure some oomfish landing can be absorbed safely, hopefully. So whole software stack has been redesigned from ground up with multiple failure points. They're not like, oh, what if this happens, I'm like, poof. No, sir. What if altimeter goes? No problem. Doppler goes? No problem. Rocket engine goes? No problem. Like, as much as failure can be handled, it will try to handle it. That's the core difference here. And landing patch was the biggest what were they thinking kind of moment. It was too tight. Basically, the target area was 500 meter by 500 meter. I'm like, wait a minute, that's too tight. Yeah, that's the problem. It literally at last moment, the command was like, okay, you have to hit here, the current decel will let you hit here, but computer tried to solve it. Problem was, it turned off the engine. It increased the speed, but here's the deal, it increased the speed at the landing phase. So even if it fired all the engine, it's like, yeah, you gonna go bam. So this patch has been given some legroom. What kind of legroom we are talking about? 4 kilometer is the length and 2.5 kilometer is the width. So there is ample legroom, meaning you just land, man. And I'm reasonably sure by this time they must have programmed such a way that's like, even if you miss this large patch, still freaking land. Just land, damn it. And to make sure the rockets don't become the limiting factor, the fuel capacity has been increased substantially. So now the engines can fire for much longer. So that's why I specified everything is designed to, like, if this goes, you still work. This is almost like a robust military kind of technology. So they have talked about mathematically what they are trying to achieve. So this is what they are trying to achieve, what we call deviation. Whenever you are collecting data from sensors and all that, there's expected value, like what kind of data you're supposed to get. So you collect all the data that you can get and then you classify it. So classification would be like, this would be the what you're most likely to get, and then there would be deviation, like a 1 standard deviation, 2 standard deviation, 3 standard deviation. Chandrayaan 2 was focused on 3 standard deviation, meaning if the data is like in this range, it's like, I got this. Now this puppy, Chandrayaan 3, is designed to handle 6 sigma, Meaning if the data is like going way too out, it will still try to understand it, not just, okay, I'm discarding it. No, I'll try to understand it, and then I'll decide whether I should discard it or not, and it will not trip out. Basically, it should not glitch out even if multiple sensors are going YOLO. That's the whole point. Everything is designed to fail, and fail. The software should still remain functional. Failure-based design. That's the software core focus. So that's the software part of it. Let's look into history to give some context. Now, why the heck software is so difficult in basically moon? Well, reality is the core limitation comes from radiation hardening. Whenever you have to talk about radiation hardening, it's not just hardware, as in like the CPU, the RAM, and all, the PCB and all that jazz. That's one part of it. You also have to worry about the software stack. It has to be designed in such a way that even a radiation hardware processor will have bit flips and glitches and all that. You just have to write the software so it can handle it adequately. So all that is super duper expensive. On top of that is super duper ancient, meaning you would be shocked to find like 200 nanometer chips are still used in like Mars rovers and all that jazz. Not even joking. So we have to use this large gates, because the moment you cross Earth's Van Allen belt, once you are outside the Earth's magneto shield, you are in a position where basically charged particles are making love, too much love, and if you have a small gate like 4 nanometer or something like that, that particle has to just go close by and it will poof 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 switch on multiple of them. So you have to have big basically junctions, so to say, that has bit more robustness. So unless the particle is super duper charged, only then it should be able to flip 1 or 2 bits, not like whole sector just went poo 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 poo. So that's why it's super duper expensive. On top of that, memory is also limited, meaning you cannot just run a giant algorithm where it's like, what if this 700, like that's also limited. Many times you will hear people say like they're running simulation of landing and then they're gonna load it up. That's what they're talking about. Like they cannot design a software landing algorithm that works on whole of the moon. To do that, you have to go to Apollo era. So like how the heck they did? They use these human. And even in that time, their calculations were so like knife on the Armstrong almost ran out of fuel when he was trying to land. So be mindful, memory is limited. So Israel Beresheet lander, this puppy, small country, big dream. They did a lot of cost cutting to get this puppy as quickly built as possible and as cheaply built as possible. Now they did the sort of hard cost cutting. That's not good or bad. Like if you have limited budget, you want to do something, you do it in that budget. However, the software was not up to the task. Not the hardware. Hardware was like glitching out, but here's the deal. You did cost cutting on that. You should expect it. So during the landing phase, the IEM inertial sensors glitched out and it got stuck. It's like, what the hell is happening? Now, in that time, it got stuck in boot loop. Like, how the heck it could be that bad? Well, here's the deal. When they launched it, they detected very early on they have messed up something badly in the core software. So they did a firmware patch, quote unquote, in space. Now, apparently that patch did not stick as well as they had thought. So when it was, the final descent phase, it reached a point where the sensor units were like giving wrong data. There's like, okay, this is wrong, something is broken, let me restart. Now here's the deal, because there was patch stuck, it did not restart correctly. So it was keep getting boot looped. And during this boot loop, rocket engine was off. So it was decelerating. It did, I think, 5 times. And then by that time, even if it had turned on, even if it had triggered the engines, it would have been too fast. It would have been like, poof, done. So be mindful. They did cost cutting, that itself is not bad, but the software stack was not robust enough. So that backfired. Then we have basically Japanese craft, Hakoto R. Now it has Suzuki in it. That's my car. So Suzuki also worked for so Japanese system, Japanese precision engineering, all that jazz. That also did the same thing. Now, how the heck this messed up? Like, this is a small system. This is Japanese. How the Japanese system can messed up? Yeah, the landing site changed, and that became an issue because of memory. So, because the memory is so limited, you only program for where you're supposed to land. And this puppy was supposed to land in a kind of flat area, which you will always design, but at the last moment, for some reason, they had to change it, and they had to land in this sort of area. And the problem with that is, when you are giving a data where you're supposed to land, you are giving a mathematical sphere of a moon, so to say. So like, this is where the moon is supposed to be. So it's using radar altimeters, like firing radars to like, where am I? So it starts to the black line, it's like, okay, this is where I'm supposed to be. But here's the deal. At the moment they were going above a cliff, as in like a crater, the lip started to come up. So radar altimeter signal started to go, okay, I'm close, I'm very close, I'm super close, I'm super duper close. And computer is like, dude, my inertial sensors are not changing. All the calculations are suggesting that cannot be, I cannot be this close to the lunar basically surface. Like data just does not line up. It turned the signal off. It's like, okay, something is wrong, let's chill down. And then it turned it on. Depth signal. Now it's like moon is way too far away compared to the black line where it's supposed to be. So that glitched out the system. System is like, what the hell is happening? And bam. So it's one of those things that you have to understand. It's super easy to say, oh, they should have done this and that. It's like nobody could figure it out that well. Like it's not Kerbal Space Program where you have it. And we do not have any moon navigation system yet. So I do expect in future that we're going to have like a really robust lunar navigation system. Only then we're going to have like successful small launches. Can we do with big? Yeah, with big system, you have enough room, enough scope where you can be like, hey, I got this. I got this. Big does give you certain advantages. But like for small things, generally it's a very what you call tedious to figure things out. Software is always the weak link. So let's talk about wisdom here. Now there are certain things that you can only learn by doing it. You have to, we call this like trial trial and error method of learning. We have to do it. It's not something that, oh, I can copy their learnings. You cannot. China tried, it cannot be done. Flat out. There are certain limitations. You cannot just like control C, control V. You cannot do that. We have to go through this. And this sort of data packet is what we classify as institutional knowledge. Now, can you, any Tom, Dick and Harry make F1 engines? In principle, yes, because F1 blueprint is available. But here's the deal. Can they actually build it? The moment they will try to build it, it will just go boom. Because there are many tweaks that are done that is not in the blueprint, but that tweaks are institutional knowledge, meaning some senior guy in NASA or some engineers senior now, but that back then they will be like, juniors, they're starting out, they're doing all that on the fly, quote unquote modification. These things become what I call institutional knowledge. It's not something that can be just like, even if you hire the people from there, unless you are hiring all of them, you're not going to get it. So institutional knowledge is not something you can copy paste. So all these things create a serious scenario where you have to go the hard way. As long as you are learning from your past experiences, you will keep growing, and success eventually become inevitable. That's the final goal. Meaning when SpaceX started, because they were actually learning from, they were not just like, okay, we gonna just use this, try to make it work. No, like, can we redesign it? Oh, we can redesign it. Oh, this will give us better probability of it. They did it, and lo and behold, they are in a position where they have 200 rocket landings. Nobody has even one landing properly done, and they have like 200. Others have like, oh, we're gonna crash it in the ocean. But they're like, dude, we got 200 landings, continuous. So be mindful. So I am happy that ISRO really looked into this, really improved their software, and now I can be damn sure when Chandrayaan 5, 6 or whatever have you, even Mars missions and all that jazz, those will be built. The software would be like, dude, you freaking land, man. I don't give a damn. Be mindful. European Union also messed up. It also had the issue where the computer thought it was below surface by 12 kilometers. It cut the parachute in the wrong time. Bam. So it's one of those things that does happen. So this is what we call, like, you have to learn it the hard way. I'm glad that ISRO is working their ass off, and I'm happy that they're improving. So what are the chances of Chandrayaan 3 succeeding? There is an old saying, thou shall not tempt fate. So I'm not going to say 100%, but it's almost certain that we're going to have a smooth, safe landing, hopefully. So this was my presentation on basically Chandrayaan 3. Hopefully you have liked it, learned from it. In that case, please hit the like button, share it amongst your friends. That will help me a lot. If you didn't like it, didn't enjoy it, I urge you to press dislike, press it twice to show me extra disappointment. Please leave a comment because I do try to reply to all of them. Subscribe, press the bell icon if you're free, and as always, thanks for watching.